Now let us discuss about disjoint set operations such as simple union and find operations. First let's see what is a disjoint set. Two sets are said to be disjoint if A intersection B equal to pi, that is if the sets doesn't have any common element. Let's take an example. Let A equal to 1, 2, 3, B equal to 4, 5, 6. So here there is no common element between A and B. So what is A intersection B? So here there is no common element. So A intersection B is pi. So now we can call these two sets as disjoint sets. Why? Because there are no common elements between the two sets. Here mainly we can perform two operations on the disjoint set. The first one is simple union, the second one is find. So in this video we are going to discuss about these two operations. We have two more operations such as weighted union and collapsed find. We will discuss those operations in the next video. First let us see about what is simple union. Simple union, we know about union. Union means combining the elements. So simply we have to join the elements. We have to append the second set elements at the end of the first set. So let A equal to 1, 2, 3, B equal to 4, 5, 6. Then what is the union? So simply we have to combine the elements. So A union B equal to 1, 2, 3, 4, 5, 6. Now let's see how that is internally implemented. Procedure to perform simple union. Let's see how we can implement simple union practically. So here totally we have 4 steps. First step is initially consider all the elements as separate trees or nodes. So if we have 6 elements, then we need to consider all the 6 elements as either separate trees or separate nodes. Second point, let P of I be the parent of each node. So every node will have some parent. So that parent is denoted by P of I. Root node's parent is -1. We know that tree means collection of nodes. The first node is called as the root node. Here root node's parent is always -1. And the last point is after each union we have to update the parent value, that is P of I. Now let's take this example. Let we have 6 elements. So 1, 2, 3, 4, 5, 6. So initially we have to consider all the elements as separate nodes or separate trees. So we have 6 nodes or 6 trees. So we have 6 trees. Here according to our choice we can perform the union operations. Here first I am performing union of 1, 2 in the first stage. Then union of 3, 4. Then union of 5, 6. So at the first stage we are performing these 3 union operations. So union of 1, 2 means 1 is the parent node and 2 is the child node. So we have to line edge like this. Arrow will be points towards the root node. So we have to point arrow towards the root node. Next if you see here union of 3, 4. So 3 is the parent node, whereas 4 is its child node. Arrow will be points towards the parent node, that is 3. Likewise we are performing union of 5, 6. So 5 is the parent node, 6 is the children node. So arrow will be points towards the parent node, that is 5. Now let's see with the help of some diagram. So here I. So I means elements. So here totally we have 6 elements, 1, 2, 3, 4, 5, 6. So here we have P of I. So P of I represents parent of that node. So here this is the first stage. These 3 diagrams represents first stage. So here the parent of 1. So parent of 1 is here, this is the parent node. So here this node doesn't have any parent. So the parent of this node is -1. If a node doesn't have any parent, so here by default this node will becomes the root node. By default this node will becomes the root node. So here what is the point here? Root node's parent is -1. So here one parent is -1. So likewise 3. this is the root node for this one. So 3's parent is minus 1. So this is the root node for this one. So 5's parent is minus 1. Next, what is the parent of 2? 1. Next, what is the parent of 4? 4 parent is 3. What is the parent of 6? It is 5. Now let us implement an operation called union of 1 comma 3. So in union of 1 comma 3. So now we have to add this tree information to the root nodes 1. So here already we have 1, 2. So for this tree we have to add 3, 4. So here we have 1, 2, 3, 1, 2. Now we have to add this 3, 4 to the 1. Now let us see what does the information of this P of I. So here 1 is nothing but root node. Root node's parent is minus 1. So here we have 1. So 1 parent's node is minus 1. Next here we have 2. So 2 parents, 3 parent is 1. So 2 parent is 1, 3 parent is 1. Likewise 4 parent is 3. So 4 parent is 3. Next for 5 and 6. So here there is no need to update any new information. So simply we have to keep the previous information only. So that is minus 1, 5. Next stage we are doing this operation union of 1 comma 5. Union of 1 comma 5. So now we have to add this tree to the root node that is 1. So already we have 1, 2, 3, 4. Already we have 1, 2, 3, 4. So for 1 we have to add 5, 6. So to 1 we have to add 5, 6. So here there is no need to change in the first 4 nodes. So 1, 2, 3, 4 just like the previous one only. Whereas coming to the 5 and 6. So 5's parent is 1, 6 parent is 5. So 5's parent is 1, 6 parent is 5. Now let's see the algorithm in order to implement simple union operation. So algorithm simple union of, it accepts 2 arguments I comma j. So I is nothing but parent node, j is nothing but child node. So here we have only one statement, that is P of I equal to j. So simply we have to store the child information in the parent. So let us take this example, algorithm simple union of 1 comma 2. So P of 1 equal to 2. P of 1 equal to 2. So this 2 information will be stored in P of 1. So only this statement is sufficient. Here the time complexity of simple union operation is big O of n. Why? Because maximum, if there are n elements, then maximum we require n minus 1 comparisons in order to perform the unions. So here the time complexity is big O of n. So it takes large amount of time in order to perform the simple union operation. So we can reduce the time complexity to some extent with the help of the weighted union that we will see in the next video. Now let us see about the second operation, that is find operation. Now let us see about find operation. So find operation is useful in order to search for an element. It returns root node if the corresponding element is available. Let us see with the help of a diagram. So here we have a tree like this. So 1 is the root node. Its children are 2, 3, 5. So 3 children is 4, 5 children is 6. So we know that we can represent this information like this. So I, so totally we have 6 elements. So 1, 2, 3, 4, 5, 6. Next, let us see the parent information. So P of I. So what is the parent of 1? Here 1 is the root node, the first node. This is called as root node. So 1 is the root node. So here we know that root node's parent value is always minus 1. 2's parent is 1. 3's parent is 1. 4 parent is 3. 5 parent is 1. 6 parent is 5. Now let us search for an element. We are searching for the element 6. So here 6 is present in the tree. So it returns root node. What is the root node here? 1. It returns the root node. Now let's see the logic here. Find of I. So here I means 6. While of P of I greater than 0. So what is I? 6. What is P of 6? So P of 6 means its value. Its value is 5. So 6 value. What is P of 6 value? It is 5. So now P of 6 will give 5. So phi is greater than 0. Yes, condition is true. So I is equal to P of I. So now I will become 5. So 6 parent node is 5. So once again control goes to the while loop. While P of I is greater than 0. So now what is I value? Now I value is 5. P of I. P of I means P of I. P of I. P of I means P of I. So P of I means 1. So 1 is greater than 0. 1 is greater than 0. Yes, condition is true. So once again body will be executed. I equal to P of 5. P of 5 is 1. So now I value is 1. I value is 1. Next once again control goes to the while loop. While P of I greater than 0. So now what is I value? 1. So what is P of 1? What is P of 1? Minus 1. So minus 1 is greater than 0. Condition is false. So control comes out from the while loop. Return I. So what is I value now? What is I value? 1. So this 1 will be returned. So this 1 is nothing but root node. So find algorithm returns root node if the corresponding element, that is key element, is available. Okay. So this is about the find algorithm. So here maximum we will require, here the time complexity is big O of n square. So maximum we will require n square comparisons. Why? Because we have a while loop. So this body will be executed maximum for n square times. Okay. So the time complexity is the time complexity for the find operation is big O of n square. So here too many comparisons are required in order to implement this operation. So we can reduce this problem, we can overcome this problem with the help of collapsed find that we will see in the next video.